Hi everybody. In this video I want to talk about the magnetic force that a magnetic field exerts on a straight segment of wire carrying a current. So here's the expression. So let's consider this segment of wire right here that's carrying a current I. In this expression, L will be the length of the segment. I is a vector representing the magnitude and direction of the current. So the magnitude of I would just be what we've been typically calling the current. But now we're considering the direction as well, so that direction would be to the right. B here is representing the magnetic field in which this current segment finds itself. Okay, so this expression, first note it's a cross product. So the force that the magnetic field exerts on this current segment of length L is given by this cross product. So the first thing to realize, this being a cross product, the direction of the force will be perpendicular to both the direction of the current and the direction of the magnetic field. How do we know which direction? Well, like all cross products, you use the right-hand rule by your favorite method. All right. The other thing we can read right off of this expression from the definition basically of a cross product is how to get that magnitude of that force vector. So like any cross product, you take the magnitude of the first vector, so we'll call this whole thing the first vector. This L times I current will have a magnitude L times I. The second vector, vector B, has a magnitude B without the arrow on it. And then we take the sine of the angle between these two vectors. So this theta here represents the angle between the current vector and the magnetic field for the particular segment in question. All right, I'll leave calculations of this nature to the homework problems or class. What I want to do is focus on finding the direction of the force on a wire segment using the right-hand rule. All right, so let's apply that formula here, and more importantly, the right-hand rule aspect of that, to find the direction of the force that this magnetic field, denoted here by little dots representing the magnetic field coming out of the board, let's find the force that direction of the force that that magnetic field exerts on each of these wire segments. So here we go. Let's look at the top segment first, which I'm calling A. We stick our fingers of our right hand in the direction of the current, and then I need to be able to curl them out to the direction of the magnetic field. So I've got to get my hand oriented the right way. Fingers in the direction of the current, curl my fingers out, and the force will be downward on this top segment. So I'm just going to label that F sub A for the direction of the force on segment A. Great. You could also use the other version of the right-hand rule. You could stick your first finger in the direction of the current. That's the first vector on here. Stick your second finger in the direction of the magnetic field. Your thumb points in the direction of the cross product, which in this case is the force. We get agreement, downward. All right. So now let's look at segment B. We have current coming down, so I put the fingers of my right hand in the downward direction. Get my hand oriented so that I can curl them out into the direction of the magnetic field. Thumb points in the direction of the magnetic force. Boom. So there's the direction of the force on segment B. Again, it's not magic. We're just using the definition of we're just using the right-hand rule, which is part of the definition of the cross product. All right, now the current segment's going this way, going to the right at the top. It's going downward here. It must be going to the left at the bottom. So in the bottom segment, if I want to find the direction of the force on that, I put my fingers in the direction of the current. I curl them outward into the direction of the magnetic field. My thumb points in the direction of the magnetic force. There we go. F sub C, that's the direction of the force on segment C. Finally, segment D, the current's heading upward. So put the fingers of my right hand in the direction of the current. Curl them into the direction of the magnetic field. Magnetic force is to the right. Now, I should have tried to draw these arrows all the same size. Now, they might not actually be all the same size. They've got different lengths. So if the same strength magnetic field and same current, and in all cases 90-degree relationship, then the longer segments will have more force on them. I may not have drawn that perfectly there. I was just mostly trying to get the direction. All right, now we might ask ourselves, would this loop have a tendency to begin to rotate? So if it starts at rest in this orientation and we only consider the magnetic forces on the segments, would it start to rotate? Well, no. What it would do is, if it's not rigid, it would like want to sort of collapse. But if you've made it rigid enough, then it could resist that collapsing. All right, so this would not start to rotate. So now let's do another example. In this example, we've got a magnetic field pointing to the right and a current loop, again in the plane of the board, where the current's going to the right at the top, it's going down on side B, it's coming to the left on side C, and it's going up on side D. So similarly oriented loop as in the first example, but a differently oriented magnetic field. All right, so let's go and find the force, the direction of the magnetic force that the magnetic field exerts on each segment of this loop, and let's go about that now. So for segment A, I've got current heading to the right, but the magnetic field's heading toward the right. So the angle between the direction of the current and the direction of the magnetic field is 0 degrees. The sine of 0 degrees is 0. Remember, theta represents the angle between the direction of the current and the direction of the magnetic field. For this top segment, that angle is 0. The sine of 0 degrees is 0. So by the magnitude expression that's part of this cross product, we get that there's no force, no magnetic force, on segment A. Likewise, let's do segment C. The current's heading to the left, while the magnetic field's heading to the right, pointing to the right. So the angle between the current and the magnetic field is 180 degrees. The sine of 180 degrees is 0, so the force on segment C is 0 as well. So you'd find it difficult to try and do a cross-producty thing because you're not able to curl your fingers from one of those vectors into the other. If you find yourself doing that, think about, oh, wait again, maybe in one of those cases where it's 0. Now you could get trapped here. You'd say, oh, I've got my current going in the direction here. I'll curl them all the way to this direction or all the way to that direction. Well, just remember, 180 degrees, the sine of that is 0. So if you're either have a current that's parallel to or anti-parallel to the direction of the magnetic field, the magnetic force on that current will be 0. Okay, so now let's look at segment B, where the current's going down. I'll put my fingers in the direction of the current, curl them into the direction of the magnetic field, and the force on segment B, on this right segment, will be out. Now you could try and draw that with an arrow, but sometimes it's easiest to write out for the direction of the force on segment B. Now let's look at the direction of the force on segment D. I stick my fingers of my right hand in the direction of the current. I curl them into the direction of the magnetic field. And I get the force on this left segment. Segment D is in. Now, you could talk about the net force on this loop, the overall loop. If the magnetic field has the same strength everywhere, and this segment, and say this segment is the same length as this segment, those in and out forces as an overall force on this loop would cancel. There'd be no net force on the loop, but there's still something interesting going on. Segment B is being pulled out, segment D is being pushed in, so you've got the loop basically going like that. It's going to start to rotate. Well, that's pretty cool. So that means there's a torque on this loop. Or another way to put it is, if there's a net torque on the loop, that means it's going to start to angularly accelerate. So if the loop is initially stationary, but you have a current running through it, it'll start to go like that. It'll start to turn. So that basically is the basis of what's behind the operation of an electric motor. Driving a loop of current in an appropriately oriented magnetic field. Now, before we close, there's one last thing I should point out. How do you actually have a current? It doesn't just magically flow. Presumably, we have some way of driving the current. So maybe not shown in here is some little power supply or some little battery that's driving current. So it's not like you just have current magically flowing forever for no reason. So these are abstractions to allow us to get at what's really going on. Of course, you've got to have some way of driving the current. Maybe a small little battery in the circuit that's not shown. Okay, thanks for watching.